Rotational kinematics. Recently in chapter 5 we studied the rotational dynamics, which is what causes objects to move in circles. In this chapter we're going to focus only on the kinematics part of it, objects going in circles. The line of motion is a circle. In this example we have this point P going along this arc from point 1 to point 2. You can make a case for this point that is moving along this arc S here, which is equivalent to the displacement x in earlier kinematics in one dimension. S here is equivalent to the displacement x. Because of the nature of this motion, you can describe the point P instead of distances along the arc. You can describe its motion by means of angle swept as it goes from one point to another. The amount of angle swept by this point P when it goes from point 1 to point 2 is the angle theta, which can be evaluated in radians to be theta in radians, be careful, it's in radians, equal the size of the arc divided by the radius, which is this equation that we have right here. Using this expression we can define the radians, by the way. 1 radian is equivalent to an arc that has the same size to the radius, which means if you want this theta here to equal 1 radian, what you need to have, you need this arc S to exactly equal the radius. When an object moves in a circle, not only we can describe it in terms of speeds, velocities, etc., we can also describe it by means of angle swept per unit time. That is known as the angular velocity. The angular velocity, by definition, we use the letter omega to describe it, is the change in angle in radians, that has to be in radians, divided by the amount of time it took the object to go from one point to another. This relationship is very equivalent to the one that we introduced in the chapter of one-dimensional kinematics. The average velocity is equal to the displacement delta x over delta t. So what is the equivalent to the displacement? Delta x. It's the angular displacement delta theta. The delta t is the same in both cases. The other important quantity that we need to describe and introduce is the angular acceleration. When an object moves around the circle and speeding up, it has an angular acceleration. Linear acceleration, early on we defined it as the change in velocity over time. In a similar way, we can define a quantity equivalent to it for rotational motions, which is called angular, which is the alpha right here, angular acceleration, which is the change in angular velocity, delta omega, over delta t. In this first example here, we have an object that is moving around a circle at constant speed all the time. If that is the case, the object will have a centripetal acceleration, and we have introduced that one early on. The centripetal acceleration is equal to v squared over r, or using the angular velocity, which is omega squared times r. If an object speeds up along the circumference of the circle, which is case B here, not only is going to have a centripetal acceleration, but it's going to have a linear acceleration along the circumference. And we called it AT. The reason we called it AT, which stands for tangential acceleration, because that acceleration is always tangent to the curve, which is the circle. Because we have two forms of accelerations, the total acceleration A, which is a vector quantity, is the sum of the AT plus the AC, the centripetal. One more time, the AT here is the linear acceleration. It is not the total. The total is A. When you add them up in this picture here using tip tail, all you need to do, take the AC and slide it over to the top right here. This is AC. And all of a sudden what you have the vector AT that starts here where the plane is, tip, then tail, tip. The acceleration of the system, the total acceleration, is that one going across. Now I would like to derive expressions that relate the linear quantities to the angular quantities, starting with the definitions that I introduced in the first slide. The theta equals the arc, the size of the arc, divided by the radius. Therefore, the arc is going to equal the radius times the theta. If you take the derivative of both sides, the change, delta S over delta T is going to equal R. R is a constant all the time, times delta theta over delta T. The theta is changing. When S changes, the theta changes. What's this expression looks like? Delta S over delta T. The delta S is the size of the arc, distance over time. That is the speed V. Is going to equal R, which is the radius times delta theta over delta T. The change of angle over time, that's the angular velocity that we have introduced a few minutes ago. Taking the derivative of this new expression one more time, you get delta V over delta T is going to equal R times delta omega over delta T. Alright, what's delta V over delta T? That's the linear acceleration. And how did we label the linear acceleration in this example? AT is going to equal R. What's the delta omega over delta T that we introduced in the previous slide? That's the angular acceleration alpha, radians per unit time squared. These two expressions that I derived for you are so useful that we will need in the near future whenever we want to convert linear speed to angular speed, and also linear acceleration AT to angular acceleration. Here is a summary of what I have derived for you in the previous slide. Alright, now we need to derive the equations for objects moving in circular motion and accelerating. Recently, we introduced it in one-dimensional kinematics, the equations for the displacement, velocity, and out of those two, we derived two more. One of them time unrelated, the other one acceleration unrelated. Those equations will continue to apply pretty much the same way. Instead of displacement x, we're going to have the equivalent to it, which is angular displacement theta. Instead of linear velocity, we're going to have angular velocity. Instead of linear acceleration, we're going to have angular acceleration. Very simple adjustment, and the equations will turn as follow. Look at this x here. What's the equivalent to it now? It's the theta right here. The v0, it's omega 0 right here. The acceleration, which is linear, is now represented by the angular acceleration. And you can make a case for the rest of the equations, and that's how you're going to apply them, and you're going to apply them exactly the same way.